So welcome to session 4. We look at the model number 4, again torsion. So in the previous session we looked at what is torsion and we derived torsion equation. So based on the torsion equation we will solve some numerical problems and look at the application of this equation. So directly we'll start with some numerical problem. So here we have a simple problem wherein we have a solid shaft which is made up of steel and it transmits a torque of 100 kilonewton meter, and the shearing stress or the shear strength of the material is given as 45 megapascal or Newton per millimeter square, and we have to find out the diameter of the shaft. So here directly we can make use of that equation, torsion equation, where that T by J is equal to tau by R. So since the shear stress is given, so here in this equation tau is taken as Fs. As I told you that different authors or different textbooks they use different notations. So the tau Fs is nothing but the shear stress or the tau in case of the formula you derived. So D is nothing but diameter of the shaft. You can take small d or capital D. T is the torque, right? And J is nothing but the polar moment of inertia. So taking that equation, T by J is equal to tau by R. So if we substitute that and if we simplify, we'll get this equation. So in this equation, in this problem, torque is given, the shear stress is given. So what is unknown is the value of diameter D. So you can simplify this equation, substitute the values, and directly we can get the value of D here. So it is 224.5 millimeter. And here you must understand that the torque is given in kilonewton meter and the stress is given in Newton per millimeter square. So you should take uniform units while calculating. So torque is given in kilonewton meter, it is converted into millimeter, and we are taking the shear stress in Newton per millimeter square. The millimeters and millimeters, the uniformity of the units is maintained. So you should be careful there with the units, and all the units should be uniform. For example, the millimeters should be there in all the formulas. It should be in millimeters only. If you take Newton, it should be there in all the formulas, Newton only. So it's kilo there. So kilo you have to take something about 10 power of 3. So that you have to simplify. You have to calculate. While calculating, you should be careful to take all these numbers correctly. Similarly, we have one more problem. Again, a solid circular shaft is there with 50 mm diameter, and it transmits a power of 150 rpm. So power when it is transmitted, the shaft rotates at some speed. So here it is 150 rpm, and the permissible shear stress is given 40 megapascal or 40 Newton per millimeter square. You will determine the power transmitted. So to calculate the power, we know that the power is 2 pi nt by 60. So in this equation we have to find out the power, and n is given, that is rpm is given 150 rpm, and the torque is unknown now, is not given directly. So before calculating the power, we should calculate the torque now. So torque you can calculate again using the torque equation, that is torsion equation. T by J is equal to tau by R. So again using that equation you can get the torque directly. So shear stress is given, tau is given. So R is nothing but D by 2, that is radius is nothing but D by 2. So substituting that, j is nothing but pi d to the power 4 by 32. Substituting that and simplifying, we get the equation for torque. And again, you should be careful, the diameter should be in millimeters, and the shear stress should be in, again it is in Newton per millimeters, no problem. So all the units are uniform. So here we'll get the answer in Newton millimeter. So torque will be getting in Newton millimeter. And in case of this equation, power equation, torque should be in Newton meter, because you have taken all the units in SI units, and when you take the torque in Newton meter, power you will get in watts or Newton meter per seconds. So to maintain the uniformity, we take the torque in Newton meter, and if you substitute that torque here, we will get the power in Newton meter per seconds, or what is called as watt. 1 watt is Newton meter joules per second or Newton meter per second. So you should be careful here while taking the units. We have one more problem here. The difference is that we are using the hollow shaft. So hollow shaft, it is having internal diameter d1 and outer diameter d2. So you can call it as di or de, d1 and d2, something like that. So here the polar moment of inertia J, so here it is taken as IP, polar moment of inertia, or you can take it as J with respect to torsion equation. So J is nothing but, as we seen in the previous case, J is for the hollow shaft will be pi d to the power 4 by minus internal diameter to the power 4 by 32. So first you calculate the J, polar moment of inertia, for the hollow shaft with respect to the outer diameter and inner diameter. So we will be getting, if the diameters are in millimeters, we will be getting in millimeter to the power 4, because it is d to the power of 4. The polar moment of inertia will be in power of 4. If you take d in meters, it will be meter to the power 4. Since we are taking d in millimeters, it is millimeter to the power 4 here. And here, depending on the given data, we have to choose the part of the equation here. So here I am using T by J is equal to G theta by L. So instead of G, here it is taken as C. Okay, so it is G here, modulus of rigidity. So it is T by J is equal to G theta by L. We are taking only this part of the equation because the data is given, theta is given, length is given, like that. So we will take the first part of the torsion equation, T by J is equal to G theta by L. Here we are not taking T by J is equal to shear stress, that is tau by R, because tau is not given, shear stress is not given. So we neglect that second part of the equation and we take the first part of the equation. T by J is equal to G theta by L. Since the value of G is given, just modulus of rigidity is given, then angle theta, that is angle of twist, is given as 1 degree and length is given as 10 meter. So depending on the given data, we have to choose that part of the torsion equation. So here you have to calculate the torque, that is T. So polar moment of inertia is calculated based on the diameters of the hollow shaft. The value of G is given, modulus of rigidity is given, the value of theta is given in degrees, and length is given in meters. So if you directly use this equation, you just substitute the values here. So while substituting the values, we should be careful. So all the units should be same. So polar moment of inertia is in millimeters, okay, and the modulus of rigidity is also in millimeters. Then theta is in degrees, so that should be converted into radians. So 1 degree means 1 into pi by 180. So you know that pi radians is equal to 180 degree. So 1 degree will be pi by 180. So always remember that the theta should be in radians. So it is given in degrees here. So that degree, the angle of twist, you have to convert it into, you have to use in radians. So 1 degree is pi by 180. And this polar moment of inertia we calculated here, it is substituted here, and length is in meters, so 10 meters. So since we have taken other values in millimeters, you have to keep length also in millimeters. So 10 meters is nothing but 10 into 1000 millimeter. So when you put all the units uniform, we get the torque in terms of Newton millimeter. If you take length in meters, then this polar moment of inertia in millimeter to the polar moment of inertia as meter to the power 4, and rigidity modulus as Newton per meter square, then you will get it as Newton meter. So you should be careful while solving the problems. So try to use uniform units. If you take millimeters in one equation, that should be there throughout the problem. If you take meters, then it should be there throughout the problem. So we have one more problem here. So this is a bit different problem, wherein we try to relate the rigidity modulus, that is elastic constants, and using these elastic constants we will calculate the other elastic constants of the material, Young's modulus and the bulk modulus. So here we have a tensile test specimen. The diameter is given, gauge length is given, and the elongation strain is given, and the load applied is given, and again a torsion test is made. So in torsion, the angle of twist is given in radians, length of the shaft is given, length of the rod is given, torque applied is given. Okay, so using this data, you have to find out the elastic modulus of the material. That is, there are 3 elastic modulus. We have seen this in the first module. We have studied about the elastic modulus of the material. So that there are 3 elastic modulus. So first one is the modulus of elasticity, second one is the modulus of rigidity, G, and third one is the bulk modulus, K. So many data, data is given here, so much of data is given. So using this data, we will first establish one by one what is required. So if you take the tensile test, in tensile test, diameter of the shaft or the rod is given, tensile load is given, length of the rod is given. So from this we can calculate the area of the cross-sectional area of the rod. So cross-sectional area of the rod is, area is pi r square, pi d square by 4. So diameter is given here 25 millimeters. So if you calculate that, you will get 491 millimeter square. So area is in millimeter square. You should remember, you should keep in mind. So once we know the area, he has given the strain. So the elongation is given here, 0.0975. So this is nothing but the elongation. So if you directly can go to the elongation equation, delta L. So this is not strain, it is elongation. Change in dimension, change in length, delta L. Elongation formula, we know that it is PL by AE. P is nothing but load applied in the tension. L is nothing but this length of the rod. A is the cross-sectional area of the rod, just now we calculated it, and E is the Young's modulus. So using this equation, based on the data given, we use this equation. So directly you can go to the elongation equation, because elongation is given here. So if you directly go to this equation, PL by AE, so in this equation, delta elongation is given, load is known, length is known, area we calculated, so you can easily find out the first elastic modulus, that is Young's modulus or modulus of elasticity, E. So in this equation, substitute all the values, So you should be careful here while substituting. So here delta L is in millimeters, load is in Newton, length you should take in millimeters, it is there, area also is in millimeters, so Young's modulus will get in Newton per millimeter square. If you calculate that, you will get the value number and the unit will be Newton per millimeter square. So Newton is because of this load N. Okay, this is 550,000 Newton. So L is in millimeters, delta L is in millimeters, area is in millimeter square. So we will get the Young's modulus, units of Young's modulus as Newton per millimeter square or megapascal. So this is the first part of the problem where the tensile data is given, and using the tensile equations, elongation and all those things, you can calculate the Young's modulus. So Young's modulus is related to tensile test, or when the rod is subjected to tensile forces. So see, the normal stress by normal strain is Young's modulus. So when you come to torsion here, so in torsion we will be calculating what is required here. So in torsion, since the shear stress is not given, and is telling us to calculate the rigidity modulus. So in torsion equation we have the rigidity modulus. So the rigidity modulus is G, and the torque is also given. So torque is given. So we take the first part of the equation, torsion equation, T by J is equal to G theta by L. So torque is given, T is known, that is polar moment of inertia you have to calculate. So the diameter is given, it's a solid shaft, so it is pi d to the power 4 by 32. Substitute this, you will get in millimeter to the power 4, and this rigidity modulus you have to find out, so just keep it as it is. Theta is given, angular twist is given in radians itself, so theta is 0.025, it is given here. Then length of the shaft, we know here it is given, it is in millimeters. So all the units keep in millimeters. The torque is in meter, so you would convert the torque in Newton meter, it's there, you have to give it Newton millimeter, so it is torque is 400 into 10 power of 3 Newton millimeter. Length is 200 millimeter. Polar moment of inertia is in millimeter to the power 4, and theta is in radians. So once we substitute the values, we will get the rigidity modulus C or G. So that will be Newton per millimeter square, just like Young's modulus. So all the modulus, the units will be Newton per meter square or Newton per millimeter square. So Newton per millimeter square is nothing but megapascal if we take the conversion. So we found out the Young's modulus and we found out the rigidity modulus G here. So he has given the Poisson's ratio here. So in the first module we have seen the relationship between Young's modulus and rigidity modulus in terms of the Poisson's ratio mu. So directly make use of that equation. So Young's modulus is related to rigidity modulus by this equation. This equation is derived in the first module. Okay, make use of that equation directly. So Young's modulus is known, rigidity modulus is known, units are same. So if you use that, you get the Poisson's ratio, which is unitless, 0.25. And coming to third modulus, that is bulk modulus. Again, we know that bulk modulus is related to Young's modulus through this Poisson's ratio mu. And also we have one more equation which relates the three modulus, that is bulk modulus, Young's modulus and the rigidity modulus. So if you don't know the Poisson's ratio, you can use that equation. So since Poisson's ratio is given here, we'll use the equation which relates Young's modulus and the bulk modulus. So here there is no rigidity modulus here. So use this equation, substitute Young's modulus is known, and all these are unitless. Mu is just now we found out, it is given here 0.25. Just now we found out this Poisson's ratio, we found out here as 0.25. So directly you can substitute here and you can get the value of bulk modulus in terms of Newton per millimeter square. So you should be careful while putting the units for all the parameters here. So again it is K is in terms of megapascal or Newton per millimeter square. So we have no problem here. So here we will find out the diameter of the shafts of the shaft, where torque is given and the shear stress is given, the angle of twist is given, and diameter of the so this is angle of twist per 20 mm diameter of the length. So here angle of twist is 1 degree over the length of the shaft. So length of the shaft is given as 20d. So length is related to diameter of the shaft here. Torque is given as 15 kilonewton meter. Shear stress is given. Then rigidity modulus is given. Angle of twist is given. So if you want to calculate diameter, so in the torsion equation we have two parts I told you. So T by J is equal to tau by R. So if you take the shear stress, the equation, that part of the equation, it is taken as strength consideration or shear stress consideration. So we take T by J is equal to tau by R. If you take tau and calculate the diameter D, it is based on strength base or strength consideration. Similarly, we have another part of the equation which relates the diameter of the shaft with respect to the angle of twist or stiffness. So angle of twist is a measure of stiffness of the material, so it is called as stiffness consideration. So based on these two considerations, two parts of the equation, you can find out the diameter of the shaft. Because diameter of the shaft will come in polar moment of inertia as well as in this part of the equation. So T by J is equal to G theta by L, T by J is equal to tau by R. So both equations, both part of the equations are used, and if you use shear stress part of the equation, it is called as strength consideration. Based on the strength consideration, diameter is derived, obtained, and also based on the stiffness angle of twist, you can calculate the diameter of the shaft. We get the value of diameter. So when you calculate the diameter of the shaft, you have to consider both the strength, shear stress, as well as the stiffness of the material. So when you do that, you get two diameters based on, one is based on strength and other one is based on stiffness. So which one is greater, that value is taken as the diameter of the shaft. So here again diameter of the shaft you have to find out. So again it is based on strength consideration as well as stiffness consideration. So here the power is given. So once the power is given, you have to use the power equation and you have to calculate the torque. Whenever power and RPM is given, you have to calculate torque. So using this equation, you calculate the torque here. So again you put all the units same. So power is in watt here, Newton meter per second. So N is in RPM. The torque will get in Newton meter. So power is in kilowatt, so that is kilo is there, so that kilo will be coming here, or else you can give it 10 power of 3 Newton meter. And coming to strength basis, T by J is equal to tau by R. So tau is the Fs is the tau here, shear stress. R is d by 2, J is pi d2 power 4 by 32. If you simplify that, you will get the torque here. And based on this, if you calculate, you get the diameter. So here you should be careful. The shear stress is taken in Newton per millimeters. It is given in Newton per millimeter square. So you will get the diameter. The torque should be in Newton millimeter. Okay, that's why the torque is converted into Newton millimeter here, and shear stress is in Newton per millimeter square. So diameter will get it in millimeter. You should be very careful while using the units, while substituting the values. Either you keep all the units in meters or you keep all the units in millimeters. So once you know the torque, you can determine the diameter of the shaft based on the strength consideration. Similarly, based on stiffness, we use this part of the equation, T by J is equal to G theta by L. So again, torque, you just calculated that J is known, then J it has diameter in that equation. So diameter you have to find out. So pi d2 power 4 by 32 is J. C rigidity modulus is given, angle of twist is given, length is given. So substitute the values, you will get diameter as 102. So out of these two diameters, one is 78 based on strength, other one is 102 mm based on stiffness. So you take one which is higher value, one which is greater. So the diameter of the shaft is 102. So while designing the shaft for this application, you should take the diameter of the shaft as 102 mm. So in the next problem, we have to find out the maximum torque. Shaft dia is given in centimeters, angle of twist is given 1.5 degree, length of the shaft is 7.5 meter. You can see that length is given in meter, diameter is given in centimeter, and the shear stress is given in millimeter square, and rigidity modulus is given in Newton per millimeter square. So you should be careful here while taking the units. So first you write down all the given units here. D is given in millimeters. You convert that into, it is given in centimeter, take it as millimeters. So take all, you can see here length is meters, 7.5 meters, take it in millimeters. Rigidity modulus is Newton per millimeter square. Angle of twist is 1.5 degree. You convert that into radians, so into pi by 180. And shear stress is in Newton per millimeter square. So directly you can go to, you can calculate the torque again with respect to two part of the equation. The first part of the equation is based on strength, where we have shear stress, all those things. So diameter is there, shear stress is given, so calculate the torque. Similarly, the other part of the equation is stiffness part of the equation. T by J is equal to G theta by L. So all the values are known. So again you can calculate the torque. So here we have two torques here, 2.23 Newton millimeter and 2.34 Newton millimeter. So which one is maximum, or which you have to consider? So for that we substitute the value of T in the stiffness equation, this equation, and we will calculate the angle of twist. So if it is less than the given angle, then it is safe. It is only checking, you have to check which torque is maximum. So if you apply 2.23 torque, the angle of twist will be less than the given, that is 1.5 degree. So it is radians. So in this we will calculate, we will substitute the value of torque 2.23 in strength. What we got the torque in strength, that torque will be substituted in stiffness equation, and we will find out the angle of theta. So angle of theta, we will get it in radians, we will get it in degrees, and sorry, you will get it in radians here, and that you have to convert it into degrees and compare that with the given twist here. So 1.43 degrees you will get. So initially you will get theta in radians, multiplied by 180 by pi, you will get it in degrees, and it is less than 1.5. If the torque, what we get from the strength consideration, if you substitute that in stiffness equation and get the angle of twist, it should be less than the mentioned angle of twist, then it is safe. Similarly, we get stiffness from the stiffness equation, we get the torque here 2.34. This will substitute in this strength equation. Okay, so if you take T from the stiffness equation and substitute it in the strength equation, strength consideration, we will calculate the shear stress. So if you calculate the shear stress, you will get 44.14 Newton per millimeter square or megapascal, and that shear stress is more than 42 which is given. So shear stress should not exceed 42, but when you put that maximum stress as 2.34, the shear stress will be more than this given stress, so it will be unsafe here. So therefore the maximum torque what you have to use is 2.23. So while designing the shaft for transmitting that power, the torque should not exceed 2.23 Newton millimeter. If you take this 2.34 as a torque, then it will fail, it will fracture, it is unsafe, because the shear stress will be more than the 42 Newton per 42 megapascal. So like this you have to check the values of torque based on strength equation as well as stiffness equation, and find out the values if they are below the limits. So if the shear stress exceeds the limit, then the shaft will fail by shear, which is unsafe when it is working, when the shaft is working. So similarly, we have next problem, we have the hollow shaft, where the power is given at 160 rpm, the angle of twist is given 2 degrees over length of 4 meter, and the shear stress is given 65 megapascal. Rigidity modulus is given, so you find out the internal and external diameter. So first you write down all the given data in same units. So here it is, power is given in Newton in kilowatts, so N is given in RPM, torque you have to find out. So initially we will get that in kilonewton meter, and that you can convert that into Newton millimeter, because we are taking other units as in millimeters. The torque is, you found the torque here. So once you find the torque, you can go to the shear strength part of the equation. T by J is equal to tau by R. So J, the polar moment of inertia for hollow shaft, is nothing but pi by 32 d to the power 4 minus di to the power 4. You know that. So just substitute that value. So we'll get d and di. So both are unknown. So here, so substitute this equation, we'll get this equation here. So this is the d is power 4 minus di to the power 4. So here we will get two equations based on this strength part of the equation. We get this part of the equation, equation 1. Then we take the stiffness part of the equation, and again we will get the value of d to the power 4 minus di to the power 4. So we'll get two equations. So one equation is here based on strength part of the equation, and one more equation we'll get based on the stiffness consideration. So based on that we'll get this equation number 2. So here we get, if we take equation 1 and 2, we'll get the value of external diameter first. So when you calculate the external diameter, we'll get it as 185 millimeters, and once we know the external diameter, we go back to this equation. So substitute the value of dE, you can get the value of dI here. So dI you can get it in millimeters. Similarly, we have the shaft which is transmitting the power at 90 kilowatt at 160 rpm. The allowable stress is given, and you have to calculate the total diameter of the shaft, and the maximum torque should not exceed the mean torque by 25%. So here in power equation we calculate the torque here, and it is taken as T mean, average torque. So it is in the problem, it is given maximum torque should not exceed 25% of the mean torque. So you can see that T max, maximum torque, should be equal to 25% of the mean torque. So in this power equation, what the torque is taken, that is the mean torque. So maximum torque should not exceed 25% of the mean torque. So it is, the maximum torque will be 1.25 times of the mean torque. So first you calculate the mean torque, and then we calculate the maximum torque by multiplying it 1.25 times. So 25% should be more than, it should not exceed 25% of the, it should not exceed the mean torque by 25%. That is the meaning here. So the meaning of that, it's written in terms of the statement is written in terms of the equation here. So the maximum torque should not exceed the mean torque by 25%. So it is 1.25 times of the T mean. So first you calculate the T max, and now this you take as torque in the strength equation. T max is taken as torque. You should not take T mean as the torque in the strength equation. You should take the maximum torque in the strength equation. So this again is T max by J is equal to tau by R. So that is the torsion equation. So here important thing is that in torque we should take the maximum torque, whereas in power we get the mean torque, and that mean torque is, you have to exceed it by 25% to get the maximum torque. That's why T maximum torque is 1.25 times of the mean torque. So that torque, what you get, maximum torque, you apply in the torsion equation and you get the diameter. So you will get 78.575 millimeter. Similarly, same problem is given, and the maximum torque should not exceed the mean torque by 20% is given here. So the maximum torque is 20% greater than the mean torque. So in the power equation we get the mean torque here first. Okay, so this mean torque you multiply it by 20%, that is 1.2 times to get the maximum torque. And this is the hollow shaft here. So once we get the maximum torque, that torque you have to use in the torque equation, in the torsion equation. So again we'll use strength consideration, and if you use maximum torque with respect to the T by J is equal to tau by R. So the radius for a hollow shaft we will take it as outer radius or outer diameter. In case of that equation, tau by R is there. So since hollow shaft we have two radiuses, two radii, so we should take the outer diameter, outer radius. So when you do that, we'll get the value of dE and dI. And also in this problem, it is related. The outer diameter is related to inner diameter. So dI is equal to 0.6 of dE. So internal diameter is 60% of the outer diameter. So using this equation, we get both the diameters based on strength. And similarly, based on stiffness, you take this part of the equation, T by J is equal to G theta by L. You calculate again dE and dI. So we'll get these two diameters. So we have one more problem here. We try to solve this problem. So it is based on the same concept. So here you have to find out the angle of twist. So we can go to the stiffness part of the equation, and you can get the theta in terms of radians, and that you have to convert that into degrees, multiplying it by 180 by pi. So that's it for this session. We will continue with the next session.